Hello, my name is Michael Durr and I'm an FAE manager at Movelis. In this presentation, I'll be discussing voltage droop, its causes and impacts, and an active droop mitigation solution. A voltage droop is an unexpected transient voltage fluctuation on a power rail that is temporary in nature. Typical causes of a voltage droop can include a change in dynamic workload, weakness in the power distribution network, and insufficient decoupling capacitance on the chip, package, or board. Why should we be concerned about voltage droops? One fundamental concern and impact of voltage droop is the erosion of timing margin. As the voltage decays, the propagation delay through logic gates will increase. If the clock period remains constant, the drooping power supply will eventually cause the logic to slow, eroding all of the available timing margin. Ones will be flopped when zeros were expected, or vice versa. This can cause undesired behavior, errors, or outright system failures. This is an example of a real-world voltage droop. Initially, there's a small amount of expected workload noise on the power supply. Then there is an event that temporarily causes a large ring with excessive voltage droops and overshoots before returning to the normal voltage level. In this zoomed-in view, we can see that some event has caused the supply voltage to ring. The nominal operating voltage is approximately 850 millivolts, with droops of about 147 millivolts and overshoots of about 100 millivolts at a frequency of 25 megahertz. The 147 millivolt droop is 17% of that nominal operating voltage, which is well below the typical VDD minus 10% sign-off corner. Such a condition could easily cause timing violations and system errors. Several passive techniques are commonly used to try to mitigate the effects of voltage droops. The easiest method is to increase Vmin, but this has the drawback of always consuming more power, and higher currents can contribute to reliability concerns. In some systems, reducing the maximum operating frequency can be an option, but this will have an obvious performance impact. Enhancing the PDN design with extra straps, wires, and vias can also be costly and create other undesirable trade-offs such as increased routing congestion. Can an active droop mitigation solution complement or replace the passive techniques? An active droop mitigation solution will need to be able to detect a voltage droop and then rapidly reduce the clock frequency to provide additional timing margin. There are several challenges in implementing and deploying an active droop mitigation solution. An active droop mitigation solution has complexities and requires expertise, time, and resources to both develop and test. Custom active droop mitigation solutions do exist in the industry, but they are usually limited to those large organizations with the necessary resources and expertise needed to handle the subtle complexities of droop detection and clock frequency manipulation. An alternative to a custom solution is a commercial IP offering, but most IP offerings are piecemeal without an integrated solution from a single vendor. An active droop mitigation solution first detects a voltage droop and then reacts to that droop by manipulating the clock frequency. These are 5 key requirements for a robust active droop mitigation solution. First, the detection and adapt time needs to be as fast as possible. The faster that a system can detect and adapt, the better it can respond to an aggressive droop event. The detect time is the time spent by the droop sensor, and the adapt time is the time taken by the clock source to reduce the clock frequency. Second, the clock frequency needs to be intelligently managed. Once the voltage droop is detected, the clock speed needs to be rapidly reduced. Then, as the droop subsides and the voltage is restored, the clock frequency needs to return to the original mission frequency in a smooth manner so that it does not self-induce another voltage droop. A programmable solution is important to provide flexibility. Each system has unique characteristics, droop events, and recovery scenarios that are uncertain at the time of a chip tapeout. An ability to adjust system settings post-silicon is vitally important to optimize droop response. Observability features will log data during droop events to provide insight to on-chip power distribution network behavior so that the severity and response to droops can be analyzed. Lastly, a turnkey solution that is integrated will provide optimal performance between droop detection and clock frequency management. This is a diagram of our integrated droop response system. Our system features a digital droop detector with a single cycle detect time with multiple programmable detection thresholds. It is built entirely from standard cells using a traditional digital design methodology. One or more droop detectors are paired with an adaptive clock generator. When the droop detector sees a droop event, it signals the clock generator, which will then rapidly reduce the clock frequency. The total system response time is no more than 3 clock cycles. The adaptive clock generator will then intelligently restore the clock back to its normal operating frequency with a smooth ramp. The ramp rate is also programmable. The system, both the droop detector and clock generator, run on core VDD voltage only. There is no need for additional higher voltage analog power rails. Both the clock generator and droop detector have observability through data logging to provide insights to the power network behavior, droop events, and droop response. To facilitate testing of our system in our test chips, we have also designed a droop injection circuit to allow us to create a wide range of droop events to test the overall system behavior. Now we can examine some simulation results of the system. We can see the overall system response in a zoomed out view. This case is applying a sinusoidal droop of 120 millivolts from an 800 millivolt nominal voltage at 1 megahertz. When the voltage droop crosses a program threshold, the clock frequency immediately reduces to 2/3 of the operating frequency. Note that this is a higher frequency than a typical divide by 2 approach. Next, the clock will start to ramp the frequency back up to an intermediate frequency point while still taking input from the droop detector about the current severity of the droop. Once the droop voltage has recovered above the threshold, the clock generator will restore the original operating frequency. In this example, a second droop occurs and the recovery process repeats. The third oscillation remains above the threshold and a droop response is not initiated. This simulation result is similar to the real-world example shown previously. A damped 25 MHz sinusoid is applied with an initial droop of 140 millivolts. We again see the rapid reduction to 2/3 of the operating frequency, followed by a ramp recovery to intermediate frequencies. When the voltage has consistently recovered above the program threshold, the operating frequency is restored. This zoomed-in view provides more detail. During the time of the highlighted rectangle, the ringing supply is causing the droop to cross the threshold and recover repeatedly. Below that rectangle, it can be seen that the adaptive clock has ramped to an intermediate frequency and is holding with hysteresis. The droop indicator has not been inactive for enough time to allow the system to make the final ramp back to the operating frequency. Once the droop indicator has stopped asserting, the frequency ramps back to the desired level. The holding and hysteresis time are also programmable parameters. In the clock frequency plot, the yellow trace is the frequency of the adaptive clock generator. The red trace is showing where the frequency would be for a divide by 2 approach. The adaptive clock will clearly have superior performance over a divide by 2. Additionally, when a divide by 2 recovers with an immediate 2x jump in clock frequency, there is a higher probability of a self-induced DIDT event and droop on the power rail. The smooth ramping of our adaptive clock generator minimizes this risk. This is a screen capture from our scope in the lab from one of our test chips. The top trace is the power rail. We can see that there is a droop event. The droop is detected and a droop indicator is asserted at the time of the left white bar. This triggers the adaptive clock to rapidly reduce the clock to a safety frequency by the time of the second white bar and is labeled as the T-adapt time. The clock then recovers to an intermediate frequency, then finally to the original mission mode frequency. Let's revisit the 5 keys to active droop mitigation. First, Our system provides a high-speed droop detection and glitch-free frequency reduction on the clock in less than 3 cycles. We intelligently recover the clock frequency with a smooth ramp to recover performance and prevent self-induced droop. The system is programmable, providing flexibility to adjust for varying droop profiles and system behavior. We have telemetry for droop response characterization and insight into the power network behavior. And finally, an integrated turnkey solution consisting of a droop detector and an adaptive clock generator designed to work together. This concludes this presentation. I'll summarize 3 takeaways. Voltage droop is a real and growing problem for large SoCs. Voltage droop will impact the power, performance, and reliability of systems, and an active droop mitigation will complement passive techniques to recover power, performance, and reliability.